Hi everyone, my name is Amir from Tohoku University and I'm presenting you a motion estimation filter for inertial measurement unit with onboard ferromagnetic materials. This work has been accepted to RAL with a presentation at ICRA conference. Inertial measurement unit is a sensory system that can help us to do the motion estimation of different systems. This sensor or measurement unit can encompass different other sensors such as a gyroscope, accelerometer, or magnetometer to record different parameters such as angular velocity to magnetic field around the sensor. The IMU can be applied to different applications such as motion capture or knowing the position and orientation of the mobile robots or their drones, as well as knowing the odometry of autonomous driving car. However, there is a serious problem known as the magnetic disturbances. These disturbances and biases can be created with different appliances such as a refrigerator or a PC, as well as the attached onboard DC motors. And these limitations are broadly covered in different studies. And for that fact, we just wanted to know how we can overcome this limitation to use the advantages of the magnetometer in motion estimation. As a result, we came up with a new idea whereby attaching certain permanent magnets near to the IMU sensor, we would like to apply a proper filter to have a better motion estimation in robots. To verify our proposed approach, we develop a following experimental setup where our goal is tracking a spherical ball with the soft ferromagnetic material inside a pipe. And to do the tracking, we have placed the permanent magnets with the attachment of the IMU sensor, where all of these soft and hard ferromagnetic materials directly affect IMU sensor. And we have a second IMU sensor as the auxiliary IMU located in outside without any permanent magnet effects, and try to show the direct location of the ball. And based on these two IMU sensors, we are trying to verify our proposed filter. Next, our design filter is mainly inspired by the Rothenberg's work, but our prediction and measurement models are developed differently. We have used a Kalman-based compensatory filter where we have our prediction and measurement models, and which they are using the different input signals from gyroscope, accelerometer, and magnetometer. Our states of the filter consists of three main states: the angular error, error of the gyroscope bias, and error of the magnetic disturbances. And we have considered different parameters such as the noise as well as the disturbances inside our signal models. Mainly, the filter model has a different structure where the prediction model has the following state transition, which consists of the second order discretized integration of the kinematics of the angular error, as well as the covariance matrix consists of the trapezoid integrations of the state transition matrix. Next, the measurement model, which is the main part where we have different measurement error inputs. It consists of the acceleration inclination error, as well as the relative errors of the acceleration and gyroscope, and the magnetometer and gyroscope estimation errors. To verify our proposed filter, we applied it to our experimental setup. This is the example recorded experiment where the solid lines presenting our proposed filter, and the dashed line is the well-known Quest filter, where you can see we have a serious deviations and biases in the Quest filter, but our filter is much more smooth without any huge deviations in the recorded angles in both of the sensors. To extend our case studies, we create 4 different cases where we have a normal angular speed with a high angular speed, and also we included 2 external disturbance cases with a noisy motor in the center as well as the heater gun, and the auxiliary sensors are as follows. Our multiple experiments showed following overall results, where we saw huge angular errors in the Quest filter and the Kalman filter without a magnetometer. It was showing that although the angular error in the auxiliary sensor was approximately small, but when there is a disturbances, which is the case C and D, there is a huge deviations in both of the filters, the classical filters. Next was our filter and Rothenberg's filter, where we were able to see that the level of the error in our proposed filter is much, much smaller. Similar behavior was observed in the Rothenberg's filter, but another interesting fact was that for the sensor with the permanent magnet attached, the accuracy of the motion estimation is much higher, where we have seen a kind of similar pattern in the Rothenberg's filter as well. And to compare our filter with Rothenberg's, here is one example recorded data where you can see the orientation is much more accurate by comparison to Rothenberg's filter, where it has serious deviations and certain sharp increases in the orientation estimation. Based on our findings, we can summarize a very important fact, where IMU sensor plus with attached permanent magnets and the proper filter design can result in better motion estimation in robust mechanisms where there is a predominant magnetic disturbances in the environment. This can be also verified with simple captured data of a magnetometer, where the sensor with the permanent magnets can shield a certain level of magnetic distortions in the environment. As the conclusion, another approach for sensor design is proposed. A compensatory filter to mitigate the magnetic disturbance and biases is developed. A better motion estimation is achieved by using the approach. In the future work, we are planning to apply the filter for faster and complex motions and orientations, and we will try to find the optimal placement of the permanent magnets in shielding the magnetic disturbances. For more details, please refer to our RA-L paper. Thank you so much for the listening.